At 3:30, the department colloquium is going to be by Bobby Kleinberg, and it'll be related in general to things we're going to learn about in class. So, last time we could have started talking about conformal prediction, at least at a high level. We could have said we could define what a nonconformity score is, how the nonconformity score is defined sort of a single parameter family of prediction sets, essentially parameterized by quantiles of that nonconformity score, and how the general premise was that you would want to come up with some or in the way that you would if somehow your underlying model was predicting something directly, and then had access to your model was providing you access to sort of these true individual probabilities, and then what the conformal prediction was going to let you do was basically take advantage of accuracy in your model to the extent that it was predicting things that looked like probabilities, but that it would sort of modify the prediction sets by making them more or less aggressive effectively, so as to get correct coverage even in the worst case signature model. Had nothing to do with the correction. Okay, so there was this idea that really you can define anything with your nonconformity. The nonconformity score is we defined it with this arbitrary function mapping features and labels real numbers. Like hopefully you designed one that has something to do with the problem at hand, but like the theory we promised was going to hold for arbitrary nonconformity scores. And the way in which we were going to use this score was to parameterize a family of prediction sets. Remember, what is a prediction set? A prediction set is like a typical classification or regression model might take as input feature vector and output the prediction for what the label would be. I think that the image is likely a car. I think that the number of inches of rainfall we're going to get tomorrow is 2.130. That's a quick prediction. A prediction set instead is intended to express uncertainty by including within it a set of labels. If I think that this thing is either a car or a van, I think that the number of inches of rain is going to be somewhere between 1.9 and so, like the kind of object we're interested in is, in general, a mapping from features to subsets of labels. This is the thing that makes it difficult to think about initially is that the range of such a function is potentially enormous. If it's a k-label classification problem, for example, there's 2 to the k possible predictions that you could output. But what conformal prediction does to simplify things from the get-go is define the single parameter family of prediction sets parameterized by this number for now. We'll generalize it later to be more expressive, but for now parameterized by this number tau, that's the single parameter. And all it does is it says, well, given n, I've got this nonconformity score. I can see the action to it, but the nonconformity score is still expecting another y. But I'll consider all of the possible y's that I can just plug into that affected argument. Okay. And I will include in my prediction set all of the possible labeled y hats that have the property that when paired with x, like it's my nonconformity score, I get something, I get a value that's below this threshold. Okay, so the single parameter tau is like a threshold on this nonconformity score. And I sort of told you in words yesterday, we'll, actually go through an analysis today, that what you should think of as tau, what you think tau is representing if your goal is to get like 90% coverage, if your goal is to have your prediction sets cover the true label on 90% of examples, you should think of tau as like a 90th percentile quantile of the distribution of nonconformity scores when I sample an XY pair from the underlying. Okay, so makes sense. And yeah, we went through a couple of examples of regression. So again, the thing we're going to prove, it's strength in general, it's going to be a coverage guarantee that doesn't care what the nonconformity score is. That's nice, and that you can design whatever nonconformity score you want, and not have to worry about coverage. It's less nice in that sort of inherent in that generality is that like we can't possibly promise that these things are useful, right? Like the nonconformity score has nothing to do with the learning problem we're trying to solve, then how could it possibly be useful? And so we went through a couple of examples just to sort of give you a taste for how you might go about thinking of coming up with a nonconformity score. Typically, the thing you would do is you would train some model, the more sophisticated, more accurate the model, the better. But some model that's trying to do something like come up with a point prediction, or maybe come up with a distribution on, predicted distribution on label. Okay. Then you sort of design your nonconformity score so that this prediction set would be like the right prediction set in the event that your model was perfect. And then you throw a sort of conformal prediction method in it, which hopefully is going to boil down to quantile estimation. But we saw two examples last time for sort of regression problems. The simplest, which didn't seem like it was going to give us particularly compelling prediction intervals, was that okay, in a regression problem, maybe you trained, like a standard sort of regression model, which we typically find by minimizing squared error. It could do a point prediction, which even if it's perfect, even if it's correct, what it's doing is it's predicting the conditional label mean. Then we did for the math, like, all right, if I'm going to produce predictions that entered at the center of the model, how wide do I have to make them? They're all going to be uniformly of the same width, so that I end up getting 90% of them. And of course, especially if distribution is continuous, there'll be a solution to this question. It's a well-posed question as I start with prediction sets with 0, and then slowly expand them out. I'll smoothly go from essentially 0% coverage to 100% coverage, and there will be some point at which I can stop and have 90% coverage. That's what that was given. But we saw that, or we argued that those prediction sets, even though, they might have something to say about the distribution because they're based on regression model, which might be pretty good, weren't super compelling, maybe as estimates of uncertainty, because they were, the way we find the nonconformity score there caused the prediction intervals to be of uniform width. Our model was sort of expressing identical uncertainty everywhere, even if that might not be the case. And one intuition for why that was that, the way we had designed the nonconformity score was not the best way to get, 90% prediction intervals, even under the presumption that our model was perfect. Our model was truly learning the thing it was trying to learn. How come? Well, because the model was learning the wrong thing. Like it was learning, even if our model was doing what it said, it was learning the mean of the label distribution given the features. And coming up with prediction intervals that have 90% coverage, that's just not a problem that is asking about means, asking about quantile. We want 90% coverage. What we want to do is we want to cut off 10% of the distribution. Right? We want the standard intervals. We want to cut off 5% of the left tail of the distribution and 5% of the right tail. And we saw once we sort of realized that okay, like if that's what you're trying to do, you can solve that problem by learning a pair of quantile regression models, one to predict the percentile of the distribution, one to predict the 90th percentile. You can define a nonconformity score that leads to, an attempt to produce prediction intervals at any point exactly defined by the 50th percentile and 90th percentile quantile. Okay. If your models were quantile regression models were correct, and you successfully learned the thing you wanted, that's the optimal threshold would recover just exactly the prediction intervals produced by your quantile regression models. But if you had failed to learn exactly the right thing, what the threshold gives us the freedom to do is to uniformly widen or contract the intervals until they get the correct number. Okay. So I just want to go through like one more example of like a sensible nonconformity score, this time in the classification setting. An example of something you could do in the classification setting, and then I'll go back to like not worrying specifically about what the nonconformity score is, just think about the bounds you can get in terms of coverage with finite data down to an English parameter. Okay, so that makes sense. Sort of mostly an overview of what we did last time. But are there questions before we begin? Yeah. That's right. Yeah. So if we're parameterizing this with only a single parameter, then the nonconformity score we defined last time in terms of like the single quantile regression model, or in terms of a pair of quantile regression models, like it has nothing clever to do if like one of them is right or another. There's variants of this that you could imagine that would only rely on a single quantile regression model, for example. You can imagine variants. But yeah, like certainly a weakness of this marginal approach is that we only have this sort of single parameter to tune once your complicated model is fixed. And when we ask for sort of more sophisticated guarantees, that's going to have to be one of the things that we start to think about that we're going to need to ask for a wider class of things we can do when trying to get coverage. So, when we revisit the conformal prediction after we've learned some more about guarantees, we'll write down more things, but cloud will now be a function of that. So, okay. Cool. So, yeah, let's try to go through the exercise of thinking about what would be a good nonconformity score in like a classification. So maybe the model you have in your head is some like image type classification problem. We're given images, there's like 1,000 labels, it could be a daisy, it could be a hot dog, officer. It's discrete then. Okay. And so the kind of thing the kind of sort of model you might train, trying to predict the label for the thing, is some kind of neural network that ultimately is going to take as input pixels of the image, and will output like 1,000-dimensional vector that at least is formatted as if it is giving you label probability. Right, like it'll give you like 1,000 numbers that are non-negative and sum to one that you are tempted to interpret as the probability that the image is a hot one. Like, of course, there's not any real sense, of course, that these are probabilities. They're just numbers formatted like probabilities. But nevertheless, a useful exercise to go through when designing a nonconformity score is to ask, suppose these were real probabilities. What would be the optimal prediction set that you could construct from these probabilities? What would be the smallest prediction set, let's say, that contains 90% of the probability mass of the labels? Okay, so let's go through that thought. Um, yeah, let's imagine. You find content, but star x y hats, which is that somehow the probability that the label y hat could come up with substitution, it's direct distribution on features and labels. Like if we are willing to allow that the thing exists, it makes sense in principle to talk about conditional distribution on the labels given features. Is kind of the thing that we're hoping we're learning when we train a neural network with some proper loss function like probability or squared error. Let's just suppose for a moment we had it. Okay, and maybe like don't worry too much about what it means that probability to don't worry. Suppose I had access to this object, and I really believed that the label was going to be drawn from this distribution. What would be the smallest set of labels that had the property that it was guaranteed to contain the true label with probability at least 90%?
Strength of probability and additively.
Exactly. Yeah, this is you know like kind of very simple hacking problem. Like probability that a set of labels contains the true label is just the sum of the probabilities of the labels contained within the set. And so, you know, the smallest subset is achieved by sort of the greedy method that sorts the labels from highest to lowest, hot dog, kielbasa, stop sign, whatever, and just in that greedy ordering start stuffing them into a prediction set until their cumulative probability exceeds 90%. Okay, it's not hard to show that if these were the real probabilities, that would be the sort of unique prediction set that minimized size, conditional on having this constraint, but it covers the label 90%. Okay, now, of course, probably don't have this object, but like, let's start from that, right? Let's think about how we would, in the language of conformal prediction, how we would like design a nonconformity store. But if we were lucky and had learned this object correctly, we would succeed in coming up with the optimal prediction set, the smallest prediction set that the labels 90%. So, you know, there's some notation. I'm going to write down some notation, but like the notation is just going to make it needlessly confusing. Again, the thing that I'm writing down is really just sort the labels from highest to lowest and stuff them in the prediction set in order, in descending order of their likelihood until you exceed 90. Okay, right. So let's say phi star x. What do you think on label? Puts them in sorted order, decreasing order of their likelihood. Okay, so it's the permutation such that probability of first label in this permutation is highest, and probability of second label is second highest, so on and so forth, and probability of the last label permutation to the sort order. Yeah.
Yeah, I suppose this won't matter too much, but I guess I would not necessarily.
If there are ties, yeah, if there are ties, I don't care how you order them and if they're right. Okay, just put them in sorted order. And again, let's give notation for the cumulative probability of some prefix of labels in this order. So notation for what is the probability that the label that we see is, somewhere between 1 and 4. Let's say that P star is ordering from 1 P minus 1 of probability being the label I. Okay, so it's like I plug in 5 here, it's like what's the probability the label is what the labels 1 through 4. Yeah. Perfect. Oh. Okay. And so then in this notation, right? But remember the prediction set we're after here, like the correct prediction set in this case, is the prediction set that just, really stuffs labels into our set in this order, right? The first label is predicated on the second label and the third label. And it stops when the set contains at least 90% of the probability amount. Okay, so if I want to write that prediction set in this form, I want to write that as saying all of the labels whose score is below some threshold. Well, how would I write that? Well, I say, okay, well, the prediction set that I'm in is the set of all labels. But when I look up what is the index of this label in the sorted order, if I look at the label, hot dog, hot dog, the first most likely label is hot dog, the 10th most likely label, the inverse of the permutation is just telling me where in the sorted order it's in. But okay, when I look up, should I include hot dog in my prediction set? Well, when I look up where in the sorted order hot dog lies, and I look at what is the cumulative probability that I get something that I got a label that is ranked before hot dog. Okay. If that cumulative probability is less than 90%, less than my target coverage probability, then I should add hot dog. Otherwise, I should. Okay. So in this notation, this is the optimal prediction set, 5 optimal predictions. Okay, so there's a good non-conformity score. Like suppose I no longer have necessarily, I no longer trust that I, have like a window into the mind of God and I can know the platonic probability that conditional on the pixels, the thing in front of the camera was a hot dog. Instead, I've trained a neural network to minimize, cross entropy, and I've got this vector. For every image, I can put like a vector of 1,000 numbers that, are non-negative in some way. Okay. I can still define this function for the vectors of numbers. Okay. If I was really good and I, learned really deeply and back propagated really hard, then maybe I learned that in which case, when I look for the threshold that's going to give me 90% coverage, that threshold will be exactly 90%, and I will produce the optimal prediction set. But there will always be some threshold that gives me 90% coverage, maybe less than 90%, maybe more, but there'll always be some threshold, because if I take this to be 1, I'll produce the trivial prediction set that contains all labels, and I'll definitely get the coverage I want. And so again, this gives me a 1-parameter family of prediction sets that will recover the optimal ones if I did a really good job of learning, but will, without needing to assume that, will always give me some collection of prediction sets that has the coverage I want. Yeah. Yeah, like if you went only to T-1, so like, you know, you included everything before hot dog. You know, the coverage probability would be strictly less than 90%. And like, then I'm not happy. I want a little more. If you want to get exactly, you're right that including hot dog might get me above 90%. If you want to get above that, if you want to get exactly, it might not be possible with the deterministic prediction set, just because there might be, you know, subset of the labels whose probability is up to exactly 90%. What you do in that case is, for the last example you're considering adding, you need to add it with some random. Okay. Does that make sense? So again, like, no theory here, like, and again, like, in general, there's no theory for the non-conformity scores of conformal prediction. The theorem we're about to prove holds for any non-conformity score. But I think this is a good recipe for coming up with them in general. Like, if only you had true probabilities, which is often the thing that, like, in principle, you're trying to learn when you train a model, you know, you can ask yourself, what is the, you know, what would be the right thing to do in that? What would, if you had access to true probabilities, what would be the correct prediction set to come up with? You can often get a pretty straightforward answer. And then, like, express it like this. Some score, in prediction set that contains all labels with some score below some threshold. Well, hey, there's your non-conformity score. Does that make sense? Okay. So, what do you actually do? Come up with a non-conformity score, and now you'd like prediction sets, you'd like them to have the correct coverage. Well, you're going to need to, we've made your problem pretty easy. There's only one thing you need to do, which is figure out what tau is, but I need to tell you how to figure out what tau is. Okay, so let's imagine that we have what I'll call a calibration set. Set of data points P that I'll imagine for now. Well, we'll also talk about the, you know, sequential adversarial version of this, but for now, let's imagine we have the distribution. Again, what I have is a sample of n points for an IID. Okay, and I want to use my sample, pick tau, and then the thing that I want to guarantee about is how once I pick tau, I've got a way of coming up with prediction sets, and what I'm interested in is the coverage that these prediction sets will have on my calibration set, but on the underlying system. Here, problem there. Okay, and so yeah, so I want to have coverage guarantees on new samples. And the guarantee, yeah, the first, maybe the thing you'll see most frequently in this literature, which I'll call marginal coverage in expectation. The guarantee that looks something like this. Not the promise that probability, and I'll write in a second what the probability is over. But you want probability that on a new example, the label is contained within the prediction set. Well, if it leads to target coverage probability, say 90%. And it shouldn't be too much more. Okay, and what we're going to be able to achieve for this kind of bound is that at least if the distribution is continuous, distribution on always for continuous, you should achieve your target coverage within an error of 1 over n plus 1. And what is this probability taken over? Well, it's a marginal guarantee in expectation. So a marginal guarantee, that means the probability is certainly taken over draw of the 2-point from the distribution. Okay, so it's got this weakness we talked about at the beginning that, you know, I'm not promising for this example that I get the answer right 90% of the time. I'm promising that I cover the label on 90% of examples, which might be this much weaker thing. That's the marginal part. And the in expectation part is that we're also taking probability over the randomness of the calibration set. And so one reason to say in expectation is an equivalent way to write this is that the quantity we're bounding here is really the expectation over the draw calibration set. Of the probability to draw a test point that the label is contained within the prediction set. And but remember, the prediction set really is a function of the calibration set. We're going to use the calibration sets to come up with the parameter count. Okay, so this is the simplest kind of bound that comes to the literature. It's very easy to prove. We'll give a very simple algorithm that keeps this bound in a moment. But what I want to emphasize is 2 things. Or we'll find out how many things. Okay, so first of all, quantitatively, this is quite a nice bound, right? Like, sort of saying our coverage, first of all, like we've not made any assumptions at all on the calibration sense. We haven't made any assumptions at all on the non-conformity. It's going to be a theorem that holds no matter what the non-conformity score is. And it's going to get out of sample very close to the target coverage. We wanted 1 minus delta. We're never worse than 1 minus delta. And we will overcover by an amount that is, it goes to 0 at a rate of 1 over n. This is a really good rate, maybe a suspiciously good rate. Because remember, when we talked about high probability out of sample bounds ago, these things like Huffington inequality and the BKW inequality, the kinds of rates were not 1 over n when we were transferring including sample bounds out of sample bounds. So they were like 1 over root n. And it wasn't because they were tight. That's right, it wasn't because our arguments were loose. Like if you flip n points, you sort of expect the empirical average really will differ from the bias by something on the order of 1 over root n. Right, so what's going on here? Well, what's going on here is that this is not a high probability bound. This is a bound that holds in expectation over the calibrations. Okay, so on any particular realization, like for any particular calibration set, you shouldn't expect to get bounds like this. This is sort of saying, okay, like sometimes you're going to overcover, sometimes you're going to undercover for some calibration set. But when you average your coverage probability over all of the calibration sets, it's going to come out just about right. Okay. So that's one thing that we might want to strengthen. If you have if for every example you have a new calibration set, every time you need to produce a prediction set, you have the luxury of coming up with a new calibration set, then maybe you can sort of empirically enjoy the expectation. But otherwise, if you're going to have a single calibration set that you use to produce many prediction sets, you're going to experience not the expected coverage, but like the coverage that is realized for a single caliber. The other thing, of course, is that this is a marginal number, so it's just promising coverage on average over example. So that's one of the things we're eventually going to want to. But the nice thing about this, super simple, and we'll see what the algorithm looks like. Super simple. Very nice quantitative benefit. Okay, here's like the basic methods, which I'll split the formal prediction. It'll take as input a calibration set D, a non-conformity score S, and a coverage target delta. And all it's going to do, it'll tune the tau. The smallest value. Such that when I look at how many points in the calibration set have non-conformity score, right? Plug in xi and yi, non-conformity score, have non-conformity score that evaluates something less than the rate of tau. I want that number of points to be at least 1 minus delta times. They're saying that tau is an empirical quantile, the non-conformity scores in the calibration set. What quantile will the feeling of 1 minus delta times plus 1? So, yeah, that's the quantile, and then we'll go out the function. That is just our standard formal prediction set function where we have chosen the value of tau or output given x, all of the labels include constant for decimal. Yeah.
I'm guessing that.
Yeah, good. This will come out of the proof, but like, let's say something about what's going on here. Intuitively, right? Like you want tau, if you want 1 minus delta coverage, you want tau to be a 1 minus delta quantile of the underlying. Okay. So like the first thing you might think is you think tau to be a 1 minus delta quantile of empirical distribution. That's almost what we're doing. As n gets large, that's closer and closer to what we're doing. The only difference is that, there's a correction of, we're looking for like a somewhat bigger quantile than we really want. This correction of, ignoring the ceiling roughly n plus 1 over n. Okay, and that's like a finite sample correction, and we'll see it'll come out of the proof why this is what we want. Okay. But think about the sort of correcting for like discretization there. The fact that we want conservative fact that we always want to be greater than 1 minus delta. But maybe to get some intuition for it, this might be needed. Think about what happens if you have like a really small number, like for a really small calibration set plus 2 points. Okay, good.
That's, like, your vision of the probability is also withdrawn calibration sets, like the calibration sets, for which probability is one, and some with occasionally probability is zero. What other, like, is there a way to characterize the underlying confusion that have like really variable?
Oh, so but I'm, like, after we do this, we'll show how to get high probability balance. It's basically, I mean, if you do, the obvious things that you still do. Find essentially the right quantile of the empirical distribution. It's just that the correct high probability bounds will have error that sort of scales like 1 over root n, not 1 over n. The algorithms be different, like we're essentially going through high probability bounds also for the same split conformal method. It's just that if you want to, the correct bound, if what you're interested in is high probability coverage guarantees given your calibration settings, it's not this. This is too strong. It's something like this where 1 over n has been replaced by 1 over square root. Yeah. Yeah, so that was what we were just talking about. So intuitively, what you want to do is come up with like the 1 minus delta quantile of the non-conformity squared. That's the value you really want on the underlying distribution. But this is a finite sample correction. Since we only have n samples, this is what's going to be the right thing to do, and you'll see why in a moment when we go through. But if you want some intuition ahead of time, think about, if n is 2, for example. Good. Other questions? But there are formal prediction. Well, I think just don't care what the distribution is, but important to the and over. Any confidence factor. Any for example, the numbers. But for simplicity, or let's that you can on non-conformity of examples drawn from the underlying distribution. This isn't really necessary, but it's going to make our lives easier. It's going to mean we don't have to worry about ties. And if you're concerned about this, observe that I can just add arbitrarily small random perturbations with non-conformity scores. I can add a little bit of Gaussian noise to them or with variance as low as I want, and then this assumption is satisfied. Okay, it's gonna help us not worry about size. And let's let our calibration set and example drawn IID. It's a little bit stronger than what we really need. We'll sort of see in the proof. The only thing we really need is that the data points we encounter be what are called exchangeable, meaning the distribution on data points, the distribution on the sequence of data points should be permutation and variance, which is a little bit weaker than IID. You'll see in the argument, we're just choosing intertrade or permutation. But morally, the version of this assumption that probably That's most often that people will think about just that the examples are independently drawn from some place. Okay. So then, if we think about the function P mapping features to some set of labels output by this method is like conformal. When fed calibration set for our object parameter, satisfies the guarantee that if I look at in expectation of the calibration set, the probability for you draw from the distribution that label like thing and my set at least one minus delta as I wanted it, and delta not too big, not larger than one minus delta plus one over. That is, you want these marginal coverage guarantees and expectations. It's as easy as just finding almost the appropriate quantile in your calibration set. Maybe with the slide shuttle that you want exactly these bounds, you want to get as small finite as you prefer. Okay, so there makes sense. We've got spherical sample of data points, and each data point has some non-conformity score. And because we hopefully assume that the distribution on non-conformity scores was continuous, probability one, they're all the same. So we don't have to worry about 2 points having the same non-conformity score. That doesn't happen. And so, what we can think about doing is sorting the points in our calibration set in increasing order of their non-conformity. So let's renumber point in our calibration set in increasing order of their non-conformity score. So by that, the point that we, the thing that we call point one, now we're going to be the thing with lowest non-conformity. And the thing that we call point two, thing with second lowest non-conformity score. And so forth, up until point n, that's the thing has CIS. And there's no ties, these are all in the unique ordering, these are all scripts inequality. So in this ordering, let's let I star that's the non-conforming for I star. how to be the smallest value satisfying this inequality. So of course, how will take value exactly equal to one of these non-conformity scores because it doesn't, we could make it even smaller. And but wouldn't have been the smallest value, right? Because how the way we defined it is always exactly equal to the non-conformity score of exactly 1 point in our calibration set. Let's name the index of that point by itself. Okay, particular like secret what I star is. I star is the feeling of 1 minus delta times plus 1. Because that's how we define how we define. Okay. We just sorted the points in our calibration set from smallest to largest, put our finger on one of them. That point was exactly the point whose non-conformity score was equal to the threshold that we chose to define our prediction. So far, so good. Okay. And so now we are interested in what is the probability over both the randomness of the calibration set and of this new point, xy, that our calibration, right, that our prediction set, when fed at it exercise input, will cover what? Okay. And what I want to use is the fact that the points in our calibration set are all distributed identically to the new point xy. All of these points were drawn IID from our distribution D. So in particular, I want to imagine data set that I'll call T prime, which is just C, my calibration set, together with one additional point, the test point added into it. Okay, this is some data set. Size n plus 1. And it consists of n plus 1 points drawn IID from the same distribution, because xy was drawn IID from the same distribution that D was drawn from, and D consisted of n plus, sorry, D consisted of n points drawn IID. And I want to, like, the thing that we're interested in is the events that y hangs within the prediction set given A. Well, when is that going to be the case? This is the case. Exactly. When the non-conformity score of this point xy will account, right? Because that's the definition of how these non-conformity scores, that's the definition of how these prediction sets are constructed. We don't have to continuous distribution, so the chances are exactly equal to 0. So it'll happen exactly when the non-conformity score is less than. That's just the definition of how these prediction sets are constructed. Okay. Well, what's that event? This is exactly that when you sort the now n plus 1 points G prime by the non-conformity scores. point, x, y, comes before. X I star y I. Right, it, the I star is the index of the point that has non-conforming score exactly found. So, you know, the event that our test point has non-conformity score less than tau is, you know, said another way, that's the event that when we sort the n+1 points by their non-conformity score, that this one comes earlier in the sorted ordering than the point I start. Right. Okay. Good. But notice that, you know, we have complete symmetry here. X, Y, our test point, is distributed identically to all of the other n points here. We've got n+1 points that are all identically distributed. Okay, so, you know, by symmetry, if we imagine sorting these points by their non-conformity scores, our test point x, y, as rank is uniformly distributed. Amongst all of the possible ranks. Equally likely that it's the first point in sorted order, the second point, the third point, all the way up to the last one. Not going to be anything different. Everything's symmetric, so any permutation of the ordering is equally likely. Okay. So what's the probability over the randomness of both the calibration set and the test point that our set covers? Like, well, it's just the probability that the test point in sorted order comes earlier than rank Einstein. Okay. Which is just I star over n+1, n+1 different ranks. We know what I star is. I star is just the feeling of 1 minus delta and n+1 for n+1. Now the ceiling only makes things bigger, so this is only larger than 1 minus delta times n+1 over n+1. The n+1 is cancelled. That's why we have the finite sample correction. And so this gives us one side of what we want is that the probability that we cover the label is only larger than 1 minus delta. Here we're explicitly using the finite sample correction. We've got n+1 in the denominator. And I think one of the spots. Next slide. So I star is now naming one of the points. But of course, if it was previously in the fifth position, like we have this ordering. I star is defined by the index of a particular point in this ordering. But now we're throwing one more point into the order that could show up anywhere. Okay, so like this particular point I star might show up one later in the ordering if our plus point. Okay, we had the fixed ordering defined by the calibration set, then we threw in one additional point. The observation was by symmetry, this additional point is equally likely to fall into each of the n+1 slots defined by the initial. Does that make sense? Okay. Good question. Then we prove the other direction as well, but it's almost the same. clothing. Again, for everything. I noticed that the argument is explicitly taking advantage of the fact that we're taking the randomness both over the calibrated set and over the test point, because we're treating everything as a random variable when we say that all orderings are equally likely. But once again, the probability over everything that we cover the test point. Well, as before, it's I star over n plus 1. That's the ceiling of 1 minus delta times n plus 1. N plus 1. But now we want an inequality in the other direction. So, you know, if we're going to take away the ceiling now, that'll make the numbers smaller. So if we want a bigger number, we need to add 1. And both 1 minus delta times n plus 1 plus 1. The worst case, the ceiling adds, you know, something really, really close to 1. And then, you know, the n plus 1 cancel here, and what we have is 1 minus delta plus 1 over. Okay, I guess covered guaranteed. The argument is really simple. It's just an argument by symmetry. Notice that we didn't really need the points to be IID. Where did we use our assumption about the distribution of points? All we used was that when we have our calibration sets and then we have our test points and we throw them together, the test point is equally likely to be in any index of the sorted order sorted by non-conformity. So that's true if the points are drawn in any geometric way. IID is one example, but all we really needed was the distribution of the calibration set together with the test point be exchangeable, which just means permutation and rank. It's a slightly weaker thing. Okay, does that make sense? Yeah. Yeah, good. So this is sort of what I was trying to say earlier, that a strength and a weakness of conformal prediction is that this theorem doesn't care what the score is. Like this theorem holds for every non-conformal. Okay, so that's nice in that whatever score you want without worrying that you're going to break coverage independently of what the non-conformity score is. Of course, if you come up with a totally useless non-conformity score, like you could come up with a non-conformity score, for example, that doesn't even look at it, might have nothing to do at all with the prediction problem. You'll still get coverage. How can that be? Well, it's because like somewhere in the design space, that if I pick a large enough threshold tau, my prediction set contain all of the labels all of the time, which gets the correct coverage, but doesn't provide you anything informative. And so, right, and so that means that the coverage guarantee on its own, yeah, but like it is what it is, but you need to, in order for this to be a useful technique, come up with useful non-conformity scores. And typically in this literature, that aspect of it is evaluated empirically, although I think the okay, so remember we sort of complained about a couple aspects of these bounds. One is this one that sort of course is gonna be generally devoted to trying to correct the fact that it's only a marginal bound, but this will on average over test points x, y, not conditionally on everything. But the other is that this was a bound in expectation over the calibration set. It says nothing at all about, for example, the variance in this coverage guarantee as a function of what the calibration set. Right, like conceivably, yeah, not the case, but conceivably, it is consistent with this theorem that, you know, for any particular calibration set, you either get 100% coverage or 0% coverage, and sort of all of the action is, you know, over the randomness of the calibration set. And, you know, if your plan was to come up with a single calibration set for which you were going to then produce lots of prediction sets downstream, this would be an unsatisfying theorem. It's true that, you know, if you averaged over all of the universes that you could exist in, on average over all of those universes, you'd get good coverage bounds, but like in the particular universe you live in, you would always get terrible coverage bounds. Okay, like that's, you know, not in fact what's going to happen, but like this theorem doesn't give you any reason to think that that's not what's going to happen. So a stronger guarantee that you might want is what we could call like calibration set conditional coverage bounds, rather than sort of asking for something that holds in expectation over the calibration set. We could ask for a theorem that holds high probability over calibration. Say, okay, I want this, you know, 99% of the time, for 99% of calibration sets that I can draw from this distribution, I should get coverage that is within some. That makes sense. It's clear why that's sort of stronger guarantee, maybe more aligned with what you might actually want if you're going to use a single calibration set to prediction set for many points. Okay. And so we basically already know how to do this. You know, remember, ultimately, what conformal prediction has done is it has just reduced this high-dimensional problem of coming up with prediction sets to this one-dimensional quantile estimation problem. Like, we'd really just like to know what is the 1 minus delta quantile of the non-conformity score distribution. And we've already, earlier last week, shown how to estimate quantities like quantiles on a data set and give bounds for how far those quantiles are from the distributional quantities we want. That was the DKW inequality. Okay, so we already know how to do that. And so we can just set up a split conformal method that we can analyze with the DKW, high probability method. The only thing we're gonna have to pay is, you know, like this particular threshold here. This was set to. This was set so that when we applied this analysis in expectation, we could get on the left-hand side here exactly 1 minus delta. We're asking for conservative guarantees where we always get 1 minus delta coverage and you know, like we don't overcover by too much. If we want to continue to have that property that with high probability we don't get under coverage and then also we don't overcover by too much, we're just going to have to like change what this threshold is to fit rather than this analysis, which is within expectation over the calibration set to fit the bounds that comes out of the KW inequality. Otherwise, it's exactly the same thing. It's just activating some empirical quantile on calibration. And let's just call this high probability split conformal. It's exactly the same thing as what we did before. Now we'll look for an empirical quantile that is larger than our target by square root of log of over gamma or gamma is going to be our high probability parameter now passed into the algorithm over 2x. Right. Why this number? Well, this was the bound that put it up in the DKW inequality, which allows us to relate in sample quantile to out of sample quantile. All right, what's the new there? Form of the new theorem is the same as the form of the old theorem. It's still going to hold no matter what the underlying data distribution was, so long as our calibration set with the ID from it. It's still going to hold for any constant parameter we care about. It's still going to hold for any non-conformity we're going to use. We're going to assume the quantities, so it's continuous, so a mild assumption. Okay, and now it's going to be a high probability bound. And so that means that what we're going to promise is something that holds with probability 1 minus gamma. Again, over the randomness of the draw of the calibration set. And what we're going to promise is that now, over the randomness of the test point, draw from the underlying district. But for a fixed calibration set, it will hold for whatever calibration set you get with the probability 1 minus gamma. For a fixed calibration set, probability that this calibration set has produced prediction set that covers our test point. Well, again, that means 1 minus delta. At most 1 minus delta plus 2 times square root of log of gamma and plus 1. Same kind of guarantee as before. We're going to get conservative coverage. We get at least 90% coverage, and it won't be too much more. But now there's two changes. One is that we're not taking the expectation over the calibration set. We're saying it's extremely likely that the calibration that you actually have in your hand has the property. Extremely likely is probably 1 minus gamma. And second, the over coverage rate now works. Before it looked like something like 1 over n. Now it looks like more like 1 over square root of n. But this is the correct quantity if what you care about is the high probability guarantees on the calibration set in your hand. The only way we were getting 1 over n in the previous analysis was explicitly by sort of taking advantage of cancellations of over coverage with some prediction sets and under coverage. But this is in a sense the right bound for like a single prediction. Is there a form of there? Okay, and this is basically just an application of the DKW inequality.
by construction. Value two quantile. Empirical. Over the calibration set, for some Q. That is, yeah, roughly one minus delta plus square root of log gamma over n. Why roughly? Well, you know, like this is you know, but like some real number, this prediction set, sorry, this calibration that only has endpoints in it, it actually only has, you know, like this is quantiles that are sort of distinct at the granularity of like 1 over n, so it doesn't really make sense to say that it's this quantile of the distribution. It's this you know, the empirical quantile that is somewhere between this and same quantity. Plus 1 over n. Quantiles include PDF, it's a step function for steps of over 1 over n. Okay. So these are the empirical quantile. But the DKW inequality tells us that probability 1 minus gamma now is prime quantile for distribution of non-conforming scores over the distribution. The underlying where Q prime, well, is roughly Q, but we may have misestimated the quantile in either direction by as much as square root of log gamma. What the DKW inequality told us, that sort of if we use our empirical samples to compute quantiles, then we'll be mostly right, except like the quantiles might be off in quantile space, but in either direction by as much as now this was exactly the amount by which we overestimated the quantiles on the empirical distribution. And so that means that if our quantile estimation error was within these bounds, which DKW tells us that it will be within with probability 1 minus gamma, then what we will have actually found was something that was at least a 1 minus delta quantile, and not more than that by more than a factor of twice this error. So that's what gives the error. The quantile estimation. Yeah. Yeah, that's right. Yeah, this is just like quantitative error. And the 2 in the theorem comes from the fact that the quantile estimation error might have been in either direction, but we already overestimated the empirical quantile by this amount, so that to get conservative. You're asking, can you relax the search change rule? Because DKW stated does require that. where it's like a little bit less clear whether this one generalizes to pain or this particular, although I wouldn't be surprised if there was a. Good. Okay. All right, so that's the basics of conformal prediction when there's distribution. I'll see you guys next week.